All right, essential chemistry for biology. So I know that you guys did not enroll in a chemistry class. You guys know that I am not a chemistry instructor. However, to be able to understand biology, we have to know a little bit of chemistry. Now, a lot of you guys are going to have very, very different chemistry backgrounds. Some of you may have taken Chem 111 here. Some of you may have not had chemistry in 20 years. That's okay. The goal of this is kind of like a review to just kind of recap some of the basics of chemistry and teach it to you as though you don't know it. That being said, I understand that chemistry is kind of very conceptual, so if I'm going too fast, if I'm skipping over things, if it's not making sense, I ask you to please tell me to slow down, okay? Ask me to stop, ask me to explain things. It's not embarrassing to speak up when it comes to this stuff, okay? So, we go. Alright, so why do we have to learn about chemistry? Essentially, everything in the entire world is a collection of chemicals. The whole world is just elements, chemicals, and compounds. And everything that you do is a result of chemical reactions occurring in the body. So every thought, every muscle movement, everything that you do is just chemical reactions. That's what gives you everything that you are and everything that all organisms are, just a series of chemical reactions. So basically, to be able to understand life, we have to understand basic chemistry. We're not going to spend the whole course talking about chemical reactions, but when we do talk about chemical reactions, you need to understand what's occurring at a molecular level to an extent. Okay? So you guys remember this picture. You've seen it twice now, right? So this one shows the organization from the biosphere all the way down to ecosystems. Ecosystems are made up of communities. Communities are made up of populations. Populations made up of organisms, organ systems, tissues, cells, organelles. And the smallest unit right here is molecules and atoms. That's the smallest unit. So this is where we're starting, essentially. Chapter 1 was more of an introduction. This is where we're going to start to understand the world of biology. So these molecules and atoms are super important because not only do those chemical reactions help you to think, they also keep you alive. They keep you living. All right. Matter. You guys probably, maybe, this for me was a definition that stuck in my head for a long time. Anything that has mass and takes up space. So matter is anything that has mass and takes up space. So this figure here kind of shows you a couple different examples of matter. You can see that matter is pretty much anything tangible. So person is matter, the butterfly is matter, the glasses are matter, the sun is matter, the clouds are matter, everything is matter. Has mass, takes up space. The next definition is mass. So mass is the measure of an amount of material in an object. I put there very clearly, mass is not the same thing as weight. Mass and weight are not the same thing, although we tend to use them interchangeably. They're not the same. An example of that is if I were to go to the moon, would I weigh less? If I were to step on a scale on the moon, would the scale read less? Yeah, it would. The gravitational pull of the moon isn't as strong as it is here on Earth, so I would weigh less. Would my mass change? No, I would still take up the same amount of space, essentially. So weight is a function of mass in regards to gravity on Earth, or gravitational pull. But mass is the amount of material in an object. Okay? It's kind of a difference there. There are 3 phases of matter that you guys need to know for this course. That's solid, liquid, and gas. There's arguably a 4th one, plasma. Don't worry about it. Solid, liquid, gas. Okay? You guys have access to the slides, right?
Yes.
Okay, cool. All right, elements. So you guys are probably familiar with this little guy up here, this periodic table, right? Everybody's favorite, but pretty much the symbol of chemistry. So this periodic table, the periodic table of elements, contains all of the different elements that there are. An element is a substance that cannot be broken down into other substances by chemical reactions. Essentially what this means is that's the smallest way that you can break something down. For example, H2O, right, water, H2O can be broken down into two H's and an O, which are both found on the periodic table. Most stuff that you deal with is some sort of compound and can be broken down to its elemental basis. Every single element that exists is found in the periodic table. So if you have a question about whether something is an element, go to the periodic table. If it's in there, it's an element. If it's not in there, it's not an element. Okay? Most of these are probably vaguely familiar to you, the ones on the top at least, because they're really common. But we don't see elements as common in nature. The one that I always kind of think of by default is gold, because gold is an element, or iron. Those are two elements. And we think of those as being really pure substances, right? That's why. So using the periodic table, you can identify a lot of stuff about a specific element, which will be important later. So you can identify the atomic number, which is shown up top in this little small number. This is the number of protons. You can identify the element symbol. Right here it's C for carbon. You can identify the atomic mass, which is located usually at the bottom and has decimal places. That's how you can tell it's the mass. Because we want mass to be precise, right? And then, so those are the big things that you get from a periodic tile, generally. And I know that you can't see them on the rest of these right here. It's because it's an example periodic table. We'll look at a real one in a little bit, okay? So humans are made up of elements, right? Because everything is made up of elements at its base. Every single thing in the world has to be made up of elements to have mass and take up space, to be matter. So on the periodic table, there are 92 elements that occur naturally. So if you were to go investigate the whole world without humans and break everything down to its ittiest little bitty pieces, you would find 92 elements. That's what the scientists have found. The rest of them, all those weird parts of the periodic table that are kind of down and to the right a little bit, those are human-made. They're not naturally occurring. 25 of these 92 elements are essential to human life. So this image here on the right lists out all 25 of these. No, you don't need to memorize all 25. But I do want you to kind of pay attention to this and conceptualize this, because there are a few I want you to know. So 4 of these make up 96% of the human body. Oxygen, carbon, hydrogen, and nitrogen. You guys have heard of all of these elements? Oxygen, hydrogen, nitrogen, carbon. That's because they're so important. They're essentially the building blocks to all of the molecules that make you up. These are the main ones used for human life. So in this picture, it kind of shows the distribution of all of these elements. So you can see oxygen, 65%, carbon, 18.5%, hydrogen, 9.5%, and nitrogen, 3.3%. That's a lot. When you think about the fact that everything that you are is just elements, that's a lot of, like, a very large percentage, you know? Like, you are, in fact, mostly oxygen and carbon. So 7 elements make up much of the remaining 4%. So if you look at this guy's socks, they're yellow, super cute. That represents the remaining 4% that's left after these elements. This includes things like calcium, phosphorus, potassium, sulfur, sodium, chlorine, magnesium. And you guys might be semi-familiar with these elements as well, because a lot of your food will say things like fortified with calcium or a great source of calcium, right? It's because these are essential elements that you need to have in your diet. If you don't get them in your diet, you're going to have a bad time. Your body won't be able to carry out the chemical reactions that it needs. And then finally, I have a vocab word for you, trace elements. So trace elements are what's at the tippy toe of the sock here. These make up a really, really tiny percentage of the elements in the body, and they are essential to life. You need them, but they're only required in super, super small amounts, and there's 14 elements here. So these ones may not be as familiar to you, except for a couple that you might recognize as taking during specific circumstances. For example, zinc, right? A lot of people take zinc when they essentially want to boost their immune system. Have you guys heard of that before? So that would be a really good example of a trace element, right? Like you need it to help boost your immune system when you're sick, or you want it to boost your immune system when you're sick. But do you need to take zinc every day of your life? Probably not. Your body does need it, but it doesn't need it in those large amounts. Another one that I want to point out here is iron and iodine. So iron and iodine are good examples of trace elements, but some people are deficient in them, right? So they have to supplement them more than other people do. And when you supplement these things, you don't need a lot. Like you're not going to see us going out and munching on iron, right? But your food, your cereal might be fortified with iron to make sure people are getting their daily iron intake, because this is really important. If you don't have enough iron, you can't get oxygen to all of the parts of your body that need it. It's important in that process. Okay? Another thing I want to just mention here really quickly is that these are the 25 that are essential for human life, but there are a lot of organisms, right? And they don't all need the same elements, and they don't all need as many as we do. So for example, most plants need about 17 elements, and they need them in different proportions too. However, for most living organisms, these four, oxygen, carbon, hydrogen, and nitrogen, are going to be the main compounds. So that is generally going to be the same. It's these trace elements and these other elements that are used in smaller doses that are going to kind of mix up a little bit. Any questions so far? All right. Compounds. So compounds are substances that contain two or more elements in a fixed ratio. Compounds are essentially going to be what you guys are more familiar with, the stuff that you interact with on a daily basis. They're a lot more common than elements in their natural form. Example of this is sodium chloride, table salt, right? Everybody's familiar with table salt. It's a combination of the element sodium and the element chlorine. You put it together in a fixed ratio, meaning 1:1, right? NaCl is NaCl. It's not Na3Cl2. It's just NaCl. That's the fixed ratio. You put those together and you get table salt. It's important to note that with compounds, when you put them together, when they're bonded together, essentially they develop all new properties. So they become different than the element in just its normal state. So sodium chloride is a good example of this, because sodium by itself, if you were to just pick it off the periodic table and have it in its true elemental form, is an explosive solid. You wouldn't want to eat that. That would be bad. Chlorine is a toxic gas. However, when you combine them together, their properties change, and it becomes sodium chloride, which you can eat safely, and it makes your food taste good. Okay? Oh, let me just mention really quick. I put the picture of water, H2O, up here too, to kind of represent that fixed ratio thing again. You never hear water being referred to as H3O5, right? It's always H2O. Because every time that water exists, it exists in this ratio, which is why I underlined the word fixed there. Because being a compound isn't just about having those two elements together, it's that to make a specific compound, they have to be present in the same fixed ratio. Okay? All right, atoms and molecules. So atoms are the smallest unit of matter that still retain the properties of an element. So essentially, if you were to have this gold ring, right? You have this gold ring. We talked about how gold is an element. If you were to take that, and you were a scientist, and you had all the tools to play with this gold ring, and you wanted to say, I want to know how small I can make this and still have it be gold. The smallest thing that you could make it is an atom. That's what an atom is. It's the smallest unit. If you broke down an atom, it would no longer be gold. It would be different pieces, right? So the individual building blocks of each atom, or of each element, are atoms. It's the smallest unit of matter that still retains the properties of that element. A molecule is a group of two or more atoms that are held together by covalent bonds. Don't worry about the covalent bonds right now. Just worry about the fact that they're held together, like two atoms that are held together form a molecule. We'll talk about covalent bonds a little bit later on. So, I like to think of atoms as the individual pieces, the building blocks, the Legos that make up each element. And then it's important to recognize that each element is made up of different types of atoms, right? If you broke down a gold ring to its smallest form, it would still be gold. If you broke down an iron, a sheet of iron, I don't know how you would buy iron. Anyway, if you broke down an iron bar to its smallest thing, it would still be iron, right? So each element has its own unique atoms. They're structurally, functionally different. So this image at the right here kind of shows a representation of atoms, molecules, and compounds. So atoms are off existing by themselves. Individual single atoms. When we are referring to an atom, we're referring to one piece. Molecules are atoms that are held together by covalent bonds. They're a group. And then compounds exist in a fixed ratio. So molecules and compounds a lot of times can be the same things, but compounds exist in a fixed ratio. Does that make sense? Okay. Here's an example of a molecule of oxygen. So oxygen is a good example of a compound because oxygen doesn't exist in nature just by itself as O. You always see people write O2, right? It's never just O. It's either oxygen or it's O2. What is your O2 levels, right? People talked about that a lot with COVID. It's because functionally oxygen hates being by itself. It likes to be matched up with another oxygen. And so when we see it in nature, when we see it in the atmosphere, when we see it in the human body, we see it as a molecule bonded to another oxygen. So it exists generally as a molecule. So this molecule is one oxygen atom plus another oxygen atom. Now, another example of the fixed ratio is O3. So that would be 3 molecules of oxygen is something that contributes to global climate change, ozone. Which is kind of interesting. All right, so the structure of atoms. So remember, atoms are the smallest building block of each individual element. These atoms are composed of what are called subatomic particles. Sub meaning below, and then atomic, right? So below the atom, you would find subatomic particles. These are the 3 subatomic particles. A proton is a subatomic particle. It's found in the nucleus, and it has a positive charge and a mass of 1 Dalton. This is a long definition. What I want you guys to, the reason why it's such a long definition is because I want you guys to be able to reference this to know all of these things. So breaking it down, a proton is a subatomic particle. It's found in the nucleus being the middle, right? You can see the nucleus right here of this atom drawing. So protons are found in the nucleus, and they have a positive electric charge. Proton positive. Makes sense? Easier to remember. So found in the nucleus, positive charge, and they have a mass of 1 Dalton. You don't need to know exactly what a Dalton is, just know that they have a mass of 1 Dalton, okay? I always remember it as just like have a mass of 1 essentially subatomic unit, because that's what a Dalton is. All right, proton, positive, in nucleus, 1 Dalton. In fact, I'll even write this on particles with a negative electric charge and negligible mass. Electrons, you can see, are not in the nucleus. And the definition does not say that. Over here, if you look at an electron, it's hanging out around the outside, traveling around, orbiting, essentially. So electrons are not in the nucleus. They have a negative charge. And I know it's harder to link together electron and negative, but just think about it as having an electric charge, right? So they have an electric charge that's negative. And they have a negligible mass. And then finally, we have neutrons. So neutrons are a subatomic particle, once again found in the nucleus of the atom, and they are electrically neutral, neutron neutral. These also have a mass of 1 Dalton. So it's important to recognize these all as very similar but very different, right? You can see now that they're listed out like this, like protons and neutrons actually have a lot in common. What's the only thing that's different? The charge, right? One has no charge and one has a charge. And then electrons are kind of like the one that stands out here is a little bit different, right? That's why electrons get a lot of the attention when we're talking about chemistry, because they exist on the outside, so they're more likely to interact with other things. And that makes sense, right? Essentially, you have this nucleus, which is like the home, the brick house that everything is staying inside of, and these electrons traveling around the outside, able to interact with other people. Everybody following this okay? All right. So this right here shows 2 different ways that you can depict an atom with all of these subatomic particles present, the protons, neutrons, and electrons. I showed you at the top the protons and neutrons are in the middle, and then the electrons are orbiting around the outside. At the bottom is an electron cloud drawing. So this once again shows the protons and neutrons in the nucleus, and then it shows the electrons in kind of like a cloud floating around, okay? So these subatomic particles, we can actually figure out how many of each of these subatomic particles exist for each element by using the periodic table. And that is where these things that I mentioned earlier, the atomic number and atomic mass, come into play. So this is where the math kind of starts for today. So if you guys have a hard time with math, I would recommend paying attention here. So elements on the periodic table get their number from the number of protons an element has. So what that means is if you have an atom that has 1 proton, right? If you have an atom that has 2 protons, one that has 3 protons, and one that has 4 protons, each one of these atoms is going to represent a different element. And it has to represent that element depending on how many protons it has. So you could use the periodic table by looking for their atomic number, and you would see that 1 on the periodic table is, I believe it's hydrogen. Is that right? 2 is helium. This is where I get lost. I don't know. What? Lithium. And
Beryllium.
B. try. So you guys understand what I'm saying there, though, essentially. The number of protons, you can count the number of protons that exist in the nucleus of the atom to figure out which element it is. This is what the atomic number is. This is how the periodic table is organized. The way that it can go from essentially 1 to 100 is because every element has to have a different number of protons. Now, you guys, so remember here how I said that a proton has 1 Dalton and a neutron has 1 Dalton. If you add together protons and neutrons, the number of Daltons that exist in a nucleus, you get what's called a mass number. So it's the sum of protons and neutrons that exist in an atom. So for example, what would the mass number be of this atom right here? 4, yeah. Now, unfortunately, all atoms don't exist with the exact same number of neutrons all the time. And this is because neutrons are neutrally charged, right? They don't have a charge. So essentially, sometimes these random, any sort of random element could accidentally acquire an extra neutron in its nucleus. Not a proton, because that would switch what the element is. But it can acquire an extra neutron. So sometimes the mass number and the atomic mass are a little bit different. But they're usually really, really, really close. So on the periodic table, the atomic mass is there. It's the number at the bottom with decimals that shows the average mass of that element out in the wild. It averages together what the mass would be of the protons and the neutrons. Because how often is this going to have an extra neutron? Not all the time, right? Depending on the element, it's probably going to be relatively rare. And so we just find the average. And that's what's located on the periodic table. This is usually located on the bottom of the periodic table. Are we following? Doing okay? Okay. So, using this logic, what element would this be? How many protons? 2, right? And then helium has 2 protons, number 2 on the periodic table. Make sense? If I lost anybody, do I need to slow down? Do I need to explain anything again? Yeah.
So the atomic mass is the right below it where it says helium.
Yep.
That's the atomic mass.
Yeah. Thank you for pointing that out. So this is the atomic mass, but the mass number is 4, right? And you see how these are actually really, really close to each other?
Yeah.
That's because occasionally out in the wild, helium is going to have this extra neutron. And that's going to bring its mass up. But you can see from this number, it's like 1 in like 2,000 that would actually happen. So it's actually quite rare for you to find a helium with an extra neutron. But since it does exist, we call the average mass right there.
Okay.
Yep. Any other questions? Okay. So, unfortunately for you, we can use all of this information to do some calculations on the periodic table, using the periodic table. So what you see over here is a periodic tile for the element sodium, Na. The number of protons we already discussed is the atomic number. What's the atomic number? 11. Yeah. Now, because protons are positively charged, electrons are negatively charged, right? Now, to kind of offset that so that an element can be stable so that your gold ring isn't shocking you all the time, we want to have the same number of protons and electrons, right, to offset that charge. So the number of electrons equals the number of protons. That being said, how many electrons would sodium have? 11. Yeah. You guys following?
Mm-hmm.
Okay. Now to get the number of neutrons, what we have to do is do a little calculation. So we have the mass number here at the bottom on the periodic table, which is 22.99. It's really close to 23, right? If we take this mass number and we subtract the number of protons, if you take the atomic mass and you subtract the number of protons, you are essentially subtracting all the Daltons from protons, and you're left with the Daltons from the neutrons. And that's how you can figure out how many neutrons exist for each element. So, how many protons are in this molecule of sodium? 11. How many electrons? 11. How many neutrons would be here? 12. Yeah, great job. Sorry, I got ahead of myself. Is anybody lost or confused? Perfect. All right. So, all right. We're going to take the element carbon, which is 6, I believe. I think it's up here on the next one. Oh, 12.011. Now, if we label all of these pieces of this periodic table, you guys understand this came from the periodic table, right? You can use the periodic table to find this information. So this is the atomic number. This also shows the number of protons. This also shows the number of electrons, because these are equal. So when you're looking at a periodic tile, you can look at this top number right here and see the number of protons and the number of electrons. This number at the bottom right here is the atomic mass. This is if you were to weigh one individual atom of that element, this is the number that you would get. And so if we go back a couple slides here, when you're weighing this, remember that the electrons have a negligible mass, right? Negligible mass. So when you're weighing this actual element, what's actually being weighed here? Where is the weight coming from?
Protons and neutrons.
Protons and neutrons. You guys follow? Protons and neutrons. So atomic mass is essentially proton mass plus neutron mass. So now to do a calculation of that, to calculate the number of one of these, you have to do a little bit of subtraction, and that's where stuff gets hairy. So to calculate, so let's start with number of protons. Using carbon right here, what would the number of protons be? 6. We follow 6 because it comes from this number right here. Number of electrons would be 6, right? Because it has to equal this because protons are positive and electrons are negative. Now this is a difficult one, the number of neutrons. How would we get this?
Atomic mass minus atomic number.
Yep, so we would take the atomic mass, which is 12.011, right, which you get from right here, and we would subtract the number of protons, which is 6. And we would get a number that's very close to 6.001. But in nature, would you see 6.011 neutrons? It's going to exist with either 6 or 7. So we're going to, for the sake of this class, you round and you say 6. You guys feeling a little better? The ones who were a little lost? If you're stuck still, feel free to stop by my office hours, talk to me in class or anything like that, and we can talk about it, okay? I understand that learning math is a little bit difficult. But I think this kind of shows you where all these numbers come from, right? Okay. All right, so taking all that we've just talked about, how many protons would one atom of gold have? You can look at the board if you need to. 79. Where did we get that number from?
Atomic number.
The atomic number, it's located at the top. Sorry all these tiles are different. I took them off the internet. I did my best. I just wasn't about to spend 3 hours trying to find identical tiles. Which of these 4 elements has an atomic mass of 65.38? Zinc, yeah. It's right there at the bottom, the atomic mass. How many neutrons does calcium have? 20. You take this 40 at the bottom, and you subtract the 20, and you get 20. Which of these elements has the atomic number 6? Carbon. And finally, how many neutrons does zinc have? 35. Do you guys see how we calculated the zinc neutrons? 65 minus 30 is 35. So, I'm giving you guys practice questions because questions like this will be on your next quiz, and I want you to be prepared for that. Another thing that I want you to know is you will need a copy of the periodic table for your next quiz. I'm going to be asking you questions as though you have a periodic table in front of you. Your text, at the end of it, like Appendix B, is that what I put on the board? Mm-hmm. Yeah. Is a periodic table. It's right here. It's actually a pretty good one, too. I mean, it's a science book, so I guess that makes sense. But it says not only the element symbols, but it says what they actually stand for underneath them, which is something that I always struggled with, was keeping those straight. So this is in your textbook. If you have the online version, you can access it as well. This is literally a screenshot of it. I just didn't screenshot all the names that are below it. Make sure you have access to one. I would recommend printing it out or having like a printed copy just so that you're not flipping between screens and stuff. The other thing that I just like feel the need to point out is that like there are some really awful people on the internet that do things like mess up periodic tables just so that students do bad on quizzes. Make sure that you're getting an accurate periodic table, okay? Use the one in the textbook, use one from a .edu, you know what I'm saying? Like don't be that like the victim of somebody going in and switching the atomic number of something or the atomic mass, and because inevitably that'll be the question I ask you on your quiz, and then you'll be upset, and I'll be upset, and everybody will be upset. We just don't want that, okay? Here's a couple more questions that you can kind of prepare yourself with. Which element on the periodic table has 14 protons? It would be number 14, right? Si? Silicon? I don't know. You see, I don't know these. That's why I like the one in the back of the book. How many neutrons does iron have? So iron is right here, 55.85. We can round it up to 56. And then we can subtract 26, which would give us 30. Yeah. So for your quiz, I will state, I won't ask you what does FE stand for, right? I will, like for this question, if it were on a quiz, I would have phrased it as how many neutrons does the element iron, Fe, have. So I don't want you to waste your time looking for that. I'm testing your knowledge of this stuff. not trivial things. Okay? Doing all right? Okay. So, as shown on the board, the number of protons determines what the element of the atom is. If it had more protons, it'd be a different element. But neutrons are a little bit more all over the place, right? Neutrons don't determine the type of element. So sometimes atoms can exist that have more neutrons than what we would expect, essentially. And these are called isotopes. So isotopes have the same number of protons and behave identically in chemical reactions. So they're pretty much the same, but they have an extra neutron. An example of this is carbon. So carbon, I want to point out here, if you have this printed off, just draw an extra electron here because this one's missing one. Internet stuff. See, that's what I'm talking about. Catch it later all the time. So carbon exists with 6 protons and 6 neutrons, right? We calculated that out on the board. 6 protons, 6 neutrons. Usually. Sometimes you'll find a carbon out in the wild that has 6 protons and 7 neutrons. Occasionally you'll find a carbon that has 6 protons and 8 neutrons, which gives these a different mass number. A different mass number than what's found on the periodic table too. Because what would the mass number of carbon-14 be? The mass number is the protons plus the neutrons. So what would the mass number of carbon-14 be? 14, right? It's actually named after its mass number. When we refer to isotopes, the number that they get is their mass number. That's how we identify them, because it shows you how different it is from the one on the periodic table. So this is an example of the nucleus, because the nucleus starts to get a little bit crowded with all those extra neutrons in there. Those are isotopes. So carbon-13 or carbon-14 are named after their mass number. Carbon-13 has 6 protons and 7 neutrons. But this is really rare and only makes up about 1% of carbon atoms. And you can tell that by looking at the periodic table, because carbon's mass number, or carbon's atomic mass, is 12.011. Now this 0.011 is coming from the presence of this 1% of carbon atoms. Because remember, the atomic mass is the average of all carbon atoms, the average weight of all of them. So 1.1% of these would be more at 13. Does that make sense a little bit? I'm not going to quiz you on that, but I think conceptually it helps to make everything click together a little bit better. So isotopes are really cool, which is essentially the reason why we're talking to them. Because sometimes isotopes are radioactive. And what that means is essentially that this nucleus, which is chock full of all these extra neutrons and doesn't have the number of protons to balance it out, is not stable. It's not happy. It does not want to exist like that. And so what happens is this nucleus undergoes what we call beta decay, and it occurs spontaneously, and it sheds off particles and releases energy. You guys have heard of radioactivity before? That's what radioactivity is. It's essentially a nucleus that has too many neutrons that's getting rid of or changing around its composition to be more stable. Carbon-14 is an example of a radioactive isotope. So this is radiation, and radiation is not necessarily something we think of as like an innately good thing, right? Like you don't want to be exposed to radiation. If you are, things happen like what happened in Chernobyl, where the nuclear reactor blew up. It released all these radioactive isotopes. Organisms picked them up, but then the shedding of this particles and energy was actually enough to cause DNA damage. DNA damage can cause consequences such as deformities like this. It can also cause cancers. So 30 people died from exposure. Thousands of people have been diagnosed with cancer. Millions of people are affected in different ways. Radioactive isotopes can be dangerous. However, they also can be incredibly useful, and they're a really cool tool for medicine and biology in general. So here is an example of that. So prostate cancer is the second leading cause of death in American men. You can see right here the distribution throughout races. It does disproportionately affect minorities as well. And so obviously that's something that a scientist or a biologist would look at, and they would say, okay, let's try and figure out a way that we can make this more effective. We don't want people dying from this. We don't want any more. We want to find a way to help these people. So a method developed sometime in the last 20 years or so essentially had the idea of using radioactive seeds made from iodine 125, so its mass number would be 125, inserted near this tumor to abolish and slow tumor growth. So on the bottom here, you can see these little tiny seeds. This is radioactive. This is a radioactive isotope, iodine 125. And the idea is that you take the tumor, you take the prostate tumor, and you insert these radioactive seeds near the tumor, and then the radioactive seeds will undergo this decay, right? They'll start shedding this energy and shedding these particles. When that happens, that can cause DNA damage, right? And we're hoping it'll cause damage to the tumor itself and stop the cancer. Does that make sense? After a few months, because obviously radioactive decay can't go on forever because it's going to run out of energy there, and it's just going until it reaches a stable form. So after a few months, it turns into its stable form, and then it's just fine. So how effective was this treatment? It was studied in 2014 with 1,000 British men. After 5 years, 94% of the people in the trial were free of cancer symptoms, which is pretty good. So a comparison study was done to see how effective this method was versus other methods. I also want to point out there is no negative control here. Last week when we talked about negative controls in cancer, some of you guys were like, oh, is that ethical? Is that ethical? These researchers deemed it not ethical to not treat cancer patients. So in lieu of a negative control, what they used was other treatment methods. Make sense? I just thought that was cool, so I wanted to point it out to you guys. So this figure shows the percentage of patients whose cancer did not progress. So cancer did not get worse, did not progress. So the seeds are in gray here, and you can see after 5 years, what was the most effective way at making sure that the cancer didn't progress? Which option? Seeds, surgery, or radiation, external radiation? External radiation was the most effective after 5 years, but just by a little bit, right? It's just a little bit over this 90 line. But the reason why a lot of times new treatment methods and medications take a long time is because look at how different that is from 10 years after treatment. What was the most effective then? Seeds by a lot, right? Next effective was surgery, and finally external radiation. So essentially what this method of treatment did is it took external radiation where you're exposing a lot of your body to potential DNA damage. And it's kind of trying to find a more concise way to use that radiation to target just the area that we care about. Does that make sense? And it seemed to work pretty well. Any questions about this? All right, so there's another use for radioactive isotopes that I want you guys to be familiar with, and it's called radiometric carbon dating. So essentially, this is a way that we use isotopes to tell how old an object is in the ground, fossils. This is used for evolution, not for medicine.
How do we know how old something is? For people, we'd ask to see their birth certificate. For trees, we count the rings. But how do we know how old a fossil is? Fossils have their own internal clock. Scientists can read it by looking at the ratio of two different types of carbon atoms. Of course, every living thing is made of carbon. Plants grab carbon dioxide from the atmosphere and use it to form complex organic molecules. Animals get their carbon by eating these plants. But there's more than one form of carbon. Most carbon atoms have 6 protons and 6 neutrons. We call this carbon-12. High up in the atmosphere, sometimes cosmic rays hit nitrogen atoms. This creates carbon with 6 protons and 8 neutrons. We call this carbon-14. Carbon-12 and carbon-14 behave alike, but carbon-14 has one unique and important attribute. It's unstable. So once an animal dies, the carbon-14 in its body will start to go away. Every 5,730 years on average, about half of the carbon-14 atoms will decay into nitrogen. This is its half-life. After one half-life, the animal will have about half the amount of carbon-14 it started with. After another half-life, it will have about a quarter. And after another half-life, it will have about an eighth. By contrast, the amount of carbon-12 it has in its body will stay the same. By measuring the ratio of carbon-14 to carbon-12, we can measure how many thousands of years have passed since the animal died. Carbon dating works for fossils up to about 60,000 years old. For older fossils, scientists use unstable elements that have much longer half-lives. For Scientific American's Instant Egghead, I'm Michael Moyer.
All right, so essentially this is a very, very different use of radioactivity and carbon in general, because remember how I said carbon was one of the most important elements in your body, right? And that's not true of just you, that's true of all living things. Now, somewhere in your body, you more than likely have some carbon-14. And that's totally fine. It's happy there as long as you're alive. But for organisms that have died, when they're in the ground, eventually those are going to decay. Eventually those are going to spontaneously undergo this radioactive decay. Now we can compare the number of carbon-14 to the number of carbon-12 to figure out how long they've been not alive, essentially. So the term that I want you to remember from here is half-life. And if you guys remember, this graph of the half-life that he gave looks kind of like this, right? Which is a little bit confusing. So I want to point out why that might be. So let's say we start with the number 100. What is half of 100? 50, right? So that's one half-life. What's half of 50? 25. That's another half-life. What's half of 25? Harder, 12.5. So this is 2, 3, and you can see how this is getting smaller every time, right? Every time it shrinks by half, it's getting smaller and smaller. But the amount of time between each of these is the same. It still takes, let's say it's 1 year. It still takes 1 year to go from here to here. It takes 1 year to go from here to here. It takes 1 year to go from here to here. It always takes 1 year for it to shrink to half its size, essentially. So you can look at the rate of this to get an idea of how old something is. Find out where it lies on this line. The other reason why I want you to be familiar with this term is because it's something used a lot in medicine. Like certain drugs will have a half-life of a certain amount of time. For example, stimulants such as ADHD medication generally have a half-life, unless you have like an extended release version, of like 8 hours, right? So 8 hours is its half-life. And we kind of use that to refer to how long something's going to be effective. But after that, it's still in your system. If you have a drug test a week later, sometimes you could, if you don't have a prescription for it, you could drop dirty because it's still in your system. It's just not affecting you to the degree it would be here. You understand what I'm saying? Because it's going down half by half by half by half. All right. Any questions there? sound like. They're essentially two atoms bonding together, attaching together. There's two different main ways that this can happen, and it's through sharing outer shell electrons, covalent bonds, or the presence of opposite charges, which is ionic bonds. We're going to talk about each of those. For your definition of chemical bonds, just know it's atoms hanging out together that are attached together. So here's an example using H2O. This is the periodic table for, or periodic tiles for hydrogen and oxygen, which are the components of H2O. And this is what the molecule looks like in nature. So essentially, when you have these, if you were to have these atoms by themselves, this would be their drawing. Hydrogen would have 1 electron sitting on the outside. Oxygen wants to have 8, right? So what it will do is it will share these electrons right here to make sure that everybody's happy. Essentially, electrons don't like to be out single in the wild. They like to be paired up. So to give oxygen the 8 electrons that it wants and to make sure this hydrogen has a match, they will come together. And we call this covalent bonding. Sharing electrons. Electrons getting married is kind of how I think about it. Electrons getting coupled up. Covalent coupling of electrons. So this is a super, super strong type of bond, and you can kind of imagine why. Because remember, these electrons exist in this orbital, right? They don't have this mass. They're kind of like out floating around. And if they're sharing this electron, they both need that electron, and so it's keeping them together because they both need to share it. It would be detrimental to either of them to break up, right? So that's a covalent bond. Covalent bonds are really strong. Yeah.
Like in the H2O, but the one with like the lines show the below it. Those are the covalent bonds, right? Like the line is the covalent bond.
The line is the bond. Yep. So ionic bonds are a little bit different, but kind of keeping the same idea. So an ionic bond is because of charges. So the opposites attract thing holds true for covalent bonds. There are two atoms that are attracted because they have an opposite charge. Now, this opposite charge kind of comes from the same sort of coupling up. Essentially, you have a metal and a nonmetal, and you can see how they both have single electrons. Electrons don't like to be single, they like to be coupled up. So the metal will it'll just give it free of charge, one electron over to this nonmetal, so that both of their electrons can be happy. It would rather have a charge than have an extra unstable electron hanging out by itself. They really want to pair up. Now, when something gets rid of an electron, they're essentially getting rid of a negative charge, right? And when you get rid of a negative charge that was perfectly balanced, the number of protons and electrons, they're now left with what type of charge? Positive. Right? Are we following this? If you get rid of an electron, which has a negative charge, then you're going to have more of a positive charge than a negative charge because you got rid of one of your negative charges. Now, this atom right here, this nonmetal, is taking on another electron. It's taking on more negative charge, which is going to give it what charge? A negative charge. So now you have one atom with a positive charge and one atom with a negative charge. These are now attracted to each other. Okay? That's an ionic bond. This is not as stable because the attraction, the compound being together, just relies on these charges. It's not actual sharing of electrons. Okay? Here's another way to visualize that with our favorite trusty NaCl. So Na has a single electron, Cl has a single electron. Sodium, Na, will just donate one, just give it away. It says, I would rather have a positive charge than I would have a single electron. So it gives it to the Cl. Now, because it gave it to them, they're positively and negatively charged, so they hang out together. They're pretty close to each other. They're not sharing that electron, they're just existing close to each other. Kind of like you mentioned, these are the different ways to represent a molecule. I just want to include a slide to show you guys this, because they could be represented in any of these ways. Sometimes we show electrons to show the bonds, sometimes we use lines, sometimes we just put the molecules on top of each other and don't show the bonds at all, and sometimes we use like sticks, okay? Just a couple different ways. When you see a molecular formula, it essentially doesn't tell you how they're attached together, so a lot of times in biology and in chemistry we use these figures so you can get an idea of what it actually looks like. Okay? Alright, polarity. Almost there, guys. Doing good. So, a molecule of water consists of oxygen and 2 hydrogens, right? But this oxygen is quite a bit bigger than these hydrogens. You guys see that? Hydrogen is 1 on the periodic table, oxygen is 8, right? So this means that oxygen is quite a bit bigger than this hydrogen. So oxygen being bigger than hydrogen is super greedy. Oxygen does not want to evenly share these electrons that they've decided to put together. You remember this stable bond made up of sharing these electrons? They come together so they're both happy. Oxygen's greedy. It wants more of the electron. When this occurs and oxygen has a harder pull on the electron because it's bigger and it gets its way, we get polarity. So what happens is because this oxygen has more electrons closer to it, it's using more of the electrons, it has a slight negative charge from this electron, from the electrons that it's pulling on. So it's not a full negative charge, it's just that the oxygen end of the water molecule right here is going to be slightly more negatively charged than the other end. Now, because the hydrogens are unhappily giving up this electron, they're going to have a slight positive charge because they're not getting the full electrons that they deserve, essentially. So polar molecules are molecules where one end is slightly positively charged, and one end is slightly negatively charged. And it's effective just electron sharing within a singular molecule. So polarity exists within a singular molecule. You guys understand this? Because the next couple slides are going to talk just about polarity and are going to require you kind of understanding the way that this works. So when this polarity exists, you have this slight positive and this slight negative charge, and we already established that positives and negatives attract using ionic bonds, right? Well, the same is true for these slight negative and slight positive charges, and we call this hydrogen bonding. Because in all honesty, the one that's going to lose the polarity fight is almost always going to be hydrogen because it's so tiny on the periodic table. It can't put up a fight at all. It just has to give in. So hydrogen bonds are a weak chemical bond that form when the polar end, the slightly positive polar end of a hydrogen atom is attracted in space to the slight negative of another polar atom. So they're essentially the consequence of polarity, the positives and negatives being attracted to each other. This is a really weak type of bond. This is not super strong, and it explains the properties of water. You can find hydrogen bonds in other molecules as well, but like this is my water bottle, right? It's liquid, there's water in here, right? But when I shake it up, you can hear the water molecules moving around, right? They move, they separate. Because the thing that holds the water together like this is hydrogen bonds. So they're a bond, it holds the water together. The water is happy existing together, touching each other. But if I shake it up, they're happy to break as well. Those are hydrogen bonds, holding individual atoms together. You guys understand what I'm saying? Doing okay? Alright. And this exists in water, or more than just water. Yeah?
So hydrogen bonds are the ones that hold atoms together?
Not all atoms, but they are there's like 3 or 4 different types of bonds, right? The ionic, the covalent, and the hydrogen bond. Hydrogen bonds are a type of weak bond that can hold a substance together, but it also allows it to kind of separate. And a really good example of that is water, which are held together by hydrogen bonds when they're sitting like this. That's what keeps my water in my water bottle and stops it from being, like a gas. But it also makes it fluid. It makes it malleable, able to move around. Yeah.
So are hydrogen bonds holding molecules together instead of atoms together, or are they also holding atoms together, like within one molecule?
So technically, like, kind of both, right? Because they're not, you wouldn't call 2 items that are hydrogen bonded, you wouldn't call that a molecule, you wouldn't call that a compound. But technically, the only reason why this attraction exists is because it's connecting this oxygen to this hydrogen. But you can still identify the separate molecules.
Okay. Got it.
Does that make sense?
Yeah, it does.
All right. That was a good question. I see where you're coming from with that. Any other questions about hydrogen bonds? Okay. So, water. Hydrogen bonds and water. Hydrogen bonds give water a lot of the qualities that we need. Water is super, super important for life. We would not be alive without water. Plants would not be alive without water. In fact, we probably would have never had life on Earth without water. There's a very, very good chance that life started in the water. If you think about what your body actually is, what your skin does, like the job of your skin is just to hold water inside of your body so that all of your life can exist in essentially a fluid system. Like inside of your skin, it is just liquidy water, right, and bones. But you get the point. So when we as humans search for extraterrestrial life, what are we looking for? Water. Because life can't exist. The life that we know can't exist without water. So this will almost certainly be a quiz question. The polarity and hydrogen bonding that exists between water molecules explains most of water's life-supporting functions. So there are some unique qualities that make water so good for supporting life. And polarity and hydrogen bonding are what essentially constitute them and make water so special and so unique. So these are the 4 big things: cohesion, temperature moderation, the low density of ice, or the fact that ice floats, and water as a universal solvent. So for cohesion, essentially what that means is exactly what it sounds like. Water molecules stick together. This is what I just talked about, kind of. My water is happy existing here as a liquid. It will stick together. They're happy. This is a product of hydrogen bonding. Now, this can be a lot more serious than just water hanging out in a water bottle. Trees, for example, depend on cohesion to transport water from the roots up to their leaves. Have you ever thought about the fact that trees take water from the ground and get it up to their leaves, but they don't have muscles? How are they doing that? They're using this property of water where it attracts each other to pull the water up to the leaves. Additionally, cohesion, or these hydrogen bonds, is responsible for surface tension. And you guys have probably seen this before with your own water. And there are insects whose whole lives essentially depend on using surface tension to travel. Super cool. This is a unique property of water and a consequence of hydrogen bonding. Next up, we have temperature moderation. So, when you go home tonight and you make your macaroni and cheese, how you have to wait an absurd amount of time for water to boil? It takes a while for water to boil. It has a pretty high boiling point. This makes it really good at moderating temperature. It requires a lot of energy for the temperature of water to change. This is good because we don't want our lakes freezing over, right? Because fish exist under there and we want to go ice fishing. We don't want our lakes freezing all the way through. We also kind of rely on this for evaporative cooling, sweating, panting, things like that, as a way to get rid of the hot liquid and keep the liquid underneath colder. That's why it takes so long to boil water. It's evaporating off the hot, like the water is doing its best to try and stay cool. Is there a question? No? The low density of ice is also a result of hydrogen bonding. And this is essentially, like, the result of it is that ice floats. So, ice floats because liquid water, essentially all of these hydrogen bonds that we talked about are constantly being reformed. They're constantly being broken and reformed. The water molecules get close together, they get far apart, right? They're just trying to find a place where they're happy. They're trying to get into a happy position. When water is frozen into ice, they essentially form stable hydrogen bonds. So you can see how this is a very clear, they're in a very, like, I don't know how to just what the word is here. But all ice is bonds that look like this next to each other. They're stable, they're happy, they're solid. You can see how this would be, sorry, not an organic chemist. That's what frozen water or ice looks like. That's how the bonds form. They get stable there. They're comfortable, they're evenly distributed in that position. Liquid water, they're closer together, but they're constantly breaking and reforming. Now this is super important, the fact that ice has a really, or the fact that ice floats, because if ice were to sink, what would happen is in the oceans or in these lakes, ice would freeze, right? It would freeze on the top, and then it would sink down. It would freeze on the top, and then it would sink down. And that would keep happening all winter, and eventually either the lake would freeze through, or you'd trap a whole bunch of animals in the middle and kill them. We don't want that. For life to be able to survive, ice has to float. Follow? Okay. And finally, the universal solvent. So water can dissolve an enormous amount of solutes and provides a medium for chemical reactions. Almost all chemical reactions can be done in water. Water is very safe. It's safe for mixing things. So this is kind of just showing you what solute, solvent, and solution mean. But water can dissolve salt ions. It can dissolve a lot of things. You know, you think about, not that most of you guys are old enough to drink, but one day when you're 21 and you drink alcohol for the first time, you're going to want something to mix it with, right? And usually that is going to be water-based. You can mix water with anything. Water is safe. And so it's the universal solvent. You can dilute things, you can, yeah. Okay? All right. So this part on acids and bases is a little bit complicated. I would just want you to know the definitions here. That acids release hydrogen ions into a solution and have a pH of less than 7. Acids release hydrogen ions into a solution, have a pH less than 7. So acids are generally going to exist like with an H in the front of them. So like HCl, because this has an H, that means that when it goes into a solution, it can turn into H and Cl. Because it has this H, in this solution, it's releasing H, which means it's an acid. Does that make sense? So if you had HF, hydrofluoric acid, this would break into H and F in a solution. Because it's releasing this, it's an acid. Okay? Now, bases, on the other hand, are a compound that wants to bond with these hydrogen ions. So there's something that wants to take up hydrogen ions. An example of that is sodium hydroxide, so NaOH. So when this breaks up, it breaks into Na plus and OH minus. Now, OH minus would love to have a hydrogen ion, because then it could be what? H2O and neutral, yeah. Right? Because OH, add another H, that's H2O. So when you see something with an OH on the end of it, generally, not always, generally that's a base. When you see something with an H on the front of it, generally, not always, it's an acid. H2O would be a good example of that, right? H2O is not an acid. But if you're trying to identify if something's an acid or a base, this is a good place to start. There are a lot of good exceptions to that, but what I want you guys to know is the potential for accepting these H's or donating these H's. Okay? So we use a scale to essentially determine how many hydrogen ions are in there. So the hydrogen ion concentration, and we call it the pH scale, which you guys are probably familiar with. I really, really like this pH scale. This is from your textbook, because it shows you, not only does it give you some real life example and show you the numbers, but it also shows you the concentration right next to it, which I think just makes it easier to understand. So, for example, super acidic solutions are going to have a lot of these hydrogen ions. That makes sense, right? Hydrogen ions, acid. So, acidic solutions have a lot of hydrogen ions floating around. Neutral solutions, ones at pH 7, are going to have a pretty even amount of hydrogen and hydroxide ions floating around. And then basic solutions are going to have more of these floating around looking for hydrogen ions. Okay? So on the pH scale, you should know that each number, so going from 1 to 2, going from 2 to 3, represents a 10-fold change in the concentration of the hydrogen ion. So what that means is that pH 2, lemon juice, has 100 times more hydroxide ions than pH 4, tomato juice. So lemon juice has 10 times more hydroxide ions than battery acid. Okay? All right, if you are ordering Starbucks and want to put in a Grubhub order, now is your time. We're almost done. So the last thing that I want to introduce related to acids and bases are buffers. Because obviously your body, your life, and the life of other living organisms is not going to be happy if you are constantly adjusting whether you're acidic or basic, right? Like, we can't just swap between those all the time. We essentially need to be steady, and life exists at a pretty neutral pH. So just about all of life has a pH close to 7 or neutral. And in humans, if your blood essentially gets super acidic or gets super basic, you'll go into a condition called either acidosis or alkalosis. Luckily for us, our blood actually functions as a buffer, which is part of the reason why that's so bad. And buffers are essentially exist in the in-between. So they exist to either offer these OHs or H's. So they have both in a big jar. So OH, H, O, that's positive. OH, H. So if you put an acid in here, now an acid is going to release a whole bunch of what? You guys remember? H plus, yeah. So if you were to put an acid in here, it would release a whole bunch of hydrogen ions, which would then happily bond with these OHs to kind of neutralize the effect of that. if you were to add a base, that's not a base, sorry. If you were to add a base to this, it would want to take up a whole bunch of hydrogen ions, but those exist in a buffer. So essentially, a buffer is some sort of combination of chemicals that allows them to exist stably in here over time, but they're ready to bond with either an acid or a base and neutralize the effect of either. So, buffers neutralize. That's like the biggest thing, is that they help neutralize the effects of either acids or bases. So it can accept the H+, or it can donate them when they're depleted. And this kind of shows you an example of that happening for either acids or bases. So buffers are not always foolproof. Sometimes they have really bad consequences. An example of that is ocean acidification. If you're familiar with climate change, you know that carbon dioxide generated by people tends to end up in the ocean. That's not a good thing. The ocean, however, has a built-up buffer system to essentially break down this carbon dioxide. But the consequence of breaking down this carbon dioxide results in a substance that competes with carbonate ions to essentially become the framework of marine calcifiers, so crustaceans, calcifiers, stuff like that. So essentially what happens is there's fewer carbonate ions, and so higher carbon dioxide in the atmosphere is causing calcifiers to be fewer, to have weaker shells. It's really interesting. I gave you guys a video on it. I'm not going to watch it right now because I know you guys want to take a break, so I just ask you to watch it at home. I posted it on Canvas. It's super interesting and kind of gives you an idea of why buffers are important, but why we also shouldn't take advantage of them.